Hey, IB Math students on Remote Monday. So we are doing the 10I notes. This was a handout that hopefully you grabbed in class if you're an in-person student on Thursday or Friday, or you can print this off the website if you are a remote student. All right, so tests for independence. Tests for independence. Let's go back to our Charles Reap table from Friday, right? Charles Reap, or Thursday if you are a seventh period student. Charles Reap was the guy in English soccer, kind of founded the modern analytics movement. And, we had a little debate on him. This is the table we looked at, and I'm sorry about this typo. This should have been 12,300, not 15,000. But this was the table from Friday. And Reap said, all right, I think that what soccer teams should do is have a small number of passes, because when there's three or less passes, they score 200 goals. And when there's more than three passes, there's only 100 goals. And since 200 is greater than 100, I think this is the way to win soccer games. And people took his advice seriously. And for decades, English soccer teams played in a certain way, and they kind of suffered for it because Reap was wrong. So those of you that were anti-Reap, I think you had the better of the arguments. And let's talk about why. All right, so we know how to calculate the probability of scoring a goal on a given possession. What is that probability? All right, well, how many goals are scored? That's the 200 and the 100, but I have the total here. That's 300. And how many total possessions were there? That's the 12,300. So I can set up a simple fraction of 300 over 12,300. And when I do that and plug it into my calculator, I get 0.0239 and then so on. So this is a 2.44 percentage chance of scoring a goal on a given possession. So what we want to know is, well, if I make three or less passes, is my percentage chance going to be greater than this? Or the same, or less? If I make more than three passes, what happens? Is the percentage chance greater, or the same, or less? That's what we want to know. What we're really asking is, does making three or less passes change my likelihood of scoring a goal? What I'm really asking is scoring goals and making a lot of passes, are they dependent or independent? That's the question I'm really asking. Does the occurrence of one change the probability of the other, either in a good way or a bad way? If so, then they are dependent. Those two variables depend on each other. If they don't make any difference to one another, that's what we call independent. So one way to think of this is to just calculate the probabilities. What's the probability of scoring a goal? Well, we just did that up here. That's the 300 over 12,300. That's the 2.44%. If you know that we made more than three passes, what's the probability of scoring a goal? Well, if you know that we made more than three passes, then this is the only data that I really care about. In that situation, there were 2,100 events, and in 100 of them, they scored a goal. So my probability fraction is the 100 over the 2,100. What's that in the calculator? Well, 100 divided by 2,100 is about 4.76%. Oh my gosh, when I make more than three passes, look what happens to the percentage chance of me scoring a goal. It doesn't go down, it goes up. That suggests that if I have less than three passes, it's probably going to be what? More than 2.44 or less. I expect it to be less, right? Because if there's a greater chance of scoring a goal with more than three, there's probably going to be a lesser chance with less than three if they're going to average to this number. So let's look at this. This is a given that less than three. What's the percentage chance that they are going to score a goal? So I'm just focusing on this data here. Oops. So 200 goals over 10,200 different possessions. What's the percentage chance? I type that into my calculator. Oh my gosh, I get 1.96%. It actually goes down if you only look at possessions that are less than three passes. So if the percentage chance changes when I accept one of the two events as a given, then it makes it pretty clear that they depend on each other. If one is true, it's going to change the probability of the other. That means that these two variables, these two events, are dependent. So this idea gives us the first test for independence. If A and B are independent events, then we would expect these probabilities to all be the same, right? We would say, well, it just doesn't matter if you have more or less passes. Doesn't matter if you have more or less. Then it's just 2.44 all the time. So if they're independent, then we expect the probability of A to be the same as the probability of A given that B has occurred, which should be the same as the probability of A given that not B has occurred. In other words, I don't care if B happens or B doesn't happen. This probability is the same no matter what. B happening doesn't change it. And we see that up here. We actually see the reverse, right? This is not true in our example up here, so that's why we know that they are dependent events. Our second test for independence follows from the work we did previously. If two events are independent, then we know that and means multiply. So we know that A and B are independent events if the probability of A and B is the same as the probability of A times the probability of B. But this works both ways. If I check the probability of A and B, and it's not the probability of A times the probability of B, then A and B are not independent events. They're dependent events. This little arrow symbol that I've drawn here is the symbol for logical equivalence. In mathematics, it's normally a little shorter than that. And sometimes just in a textbook, you'll see a double bar like this. That's a little prettier. This means if this is true, this is true. If this is true, this is true. They kind of go both ways logically. So in other words, the conditional and its converse are both true. That'll end the first part.